The YF-23 lost the military's most famous competition to the F-22, yet engineers still whisper the wrong jet won. Back in the 1980s, the emergence of highly advanced Soviet interceptors directly threatened the long-standing air superiority of the F-15. At the exact same time, sophisticated surface-to-air missile systems were rapidly proliferating, making the skies exceptionally lethal for conventional aircraft. Facing these dual threats, the Air Force outlined the Advanced Tactical Fighter program. They demanded a jet capable of sustained supercruise and comprehensive stealth. These requirements marked a shift in U.S. doctrine, prioritizing a pilot's ability to strike from the shadows over their ability to win a turning fight. Northrop approached this problem by designing an uncompromising jet-powered missile. They built the YF-23 strictly for beyond visual range engagements, striking targets before ever being seen. Lockheed took a different path with the YF-22. They willingly sacrificed a fraction of range and stealth to guarantee dominance in close-range dogfights. This left the Air Force with a difficult choice: take a radical leap into unproven long-range stealth theory, or choose a safer hedge that retained traditional maneuvering capabilities. Before we examine the classified mechanics that made these jets so different, subscribe to the Global Warwatch Network for more aerospace analysis. The military's ultimate selection of the YF-22 reveals exactly how much risk the Pentagon was willing to tolerate for the future of air combat. The YF-23 utilized a highly unique shape to evade radar, relying on a blended wing body and symmetrically swept diamond wings. It featured an all-moving Pelican V-tail. By eliminating traditional vertical stabilizers, Northrop removed right-angle surfaces that typically generate large radar returns. This profile meant the YF-23 bled little energy in sustained turns, but surrendered the extreme high angle of attack maneuverability seen in the YF-22. Feeding air to the engines presented another challenge. Traditional splitter plates separate turbulent air from the fuselage, but they also create deep cavities that reflect incoming radar waves. Northrop solved this by installing microperforated gouging panels directly into the skin ahead of the intake lips. This active suction system pulled the turbulent boundary layer air away, allowing the inlet to remain seamlessly blended into the fuselage while still feeding stable air to the engines. These aerodynamic innovations achieved impressive supercruise efficiency, but they forced the Air Force to rely on flight mechanics that remained largely unproven in combat. For heat management, Northrop entirely omitted heavy thrust vectoring nozzles to prioritize weight savings and stealth over agility. Instead, the YF-23 routed its exhaust into flat, open troughs positioned along the top deck of the rear fuselage. These troughs were lined with lamelloid tiles. This system pushed cool engine bleed air through thousands of micropores to rapidly dissipate exhaust heat, shielding the jet from infrared missiles. This speed and stealth approach stood in stark contrast to the YF-22, which relied on thrust vectoring nozzles to achieve dramatic low-speed agility. To power the jet, Northrop tested the General Electric YF-120 engine. It featured a variable cycle design, acting as a fuel-efficient turbofan at low speeds and shifting into a turbojet for supersonic flight. This engine enabled the YF-23 to reach a supercruise speed of Mach 1.6 while maintaining a combat radius of roughly 1,200 nautical miles. Despite the performance, the Air Force rejected the YF-120 for the simpler Pratt & Whitney YF-119, citing concerns over the technical risk of the variable cycle hardware. This combination of low infrared visibility and high-speed supercruise successfully realized the ghost-like interceptor concept, but it relied on hardware the Air Force viewed as a major production risk. That mechanical complexity extended to the internal weapons carriage, which Northrop designed as a single, cavernous, deeply stacked bay. Stacking weapons introduced a severe mechanical hazard. If a lower-tier missile jammed during launch, every weapon stacked above became unusable. Lockheed avoided this by utilizing shallower, wider bays, guaranteeing every missile could fire independently without a single failure blocking the others. Northrop was already fighting an uphill battle regarding manufacturing risk. To save money during prototyping, they used commercial off-the-shelf landing gear from F-15s and F-18s. The political reality was even tougher. Northrop was currently under congressional scrutiny for massive cost overruns and delays on the B-2 Spirit bomber program. While Northrop conducted cautious flight evaluations, Lockheed executed aggressive, dynamic demonstrations that included successful live missile firings from the YF-22. Lockheed also had a highly visible track record of success with the F-117 program, which gave the Pentagon greater confidence in their ability to manage the program. The Air Force ultimately selected the YF-22 because they trusted the independent weapons layout and Lockheed's ability to deliver a mature combat-ready platform. Looking at this quadrant chart, we plot the YF-22 in a clear, high-agility, moderate-risk zone, perfect for traditional dogfight doctrine. When we plot the YF-23, it pushes stealth and range boundaries, landing deeply in the red, high mechanical risk quadrant. There is a specific operational scenario where the YF-23 would have been undisputed, operating strictly as a long-range, high-speed, invisible sniper covering massive theaters like the Pacific. The military rejected this in 1991, but Northrop's tailless aerodynamic philosophy is now the exact foundation for sixth-generation fighters. Thank you for watching.